way. Anyway, well, let's recall a few things from last time. Working. So there is, well, there are several ways to think about connections, and well, that's one way which which works for vector bundles and can be adapted to other types of bundles. And there's another way which we started to talk about, but didn't quite finish. So let's do this. Let's do this today. The idea of a connection is the same as the idea of the covering homotopy property in homotopy theory. In fact, I don't know exactly how Jean-Pierre Serre came up with the covering homotopy property, but I suspect that the main inspiration was the idea of a connection from differential geometry. Okay, so let me explain the second definition in more detail. Basically, we will need to be able to say that a connection on a principal bundle induces a connection on an induced bundle, and if the action of the group is on the action of the structure group on the fiber of the induced bundle is transitive, faithful, then conversely, a connection on the induced bundle gives one a connection on the principal bundle. And there are two ways to go from one type of connections to other type of connections. One is via formulas, and this is not exactly illuminating. So we want to have another another way of thinking about connections. But on the other hand, we will need the first definition to define the Dirac operator. Not because the second definition doesn't work, but because that's the only way that I know how to define the Dirac operator. So there may be a better way, but I'm just not aware of. Okay, so the second definition in more detail. We start with we start with the fiber bundle with structure group G, which acts on, on the fiber F. On the well, let's assume that everything is smooth. The group, the projection, the base, and so on. Reaction of the group on the fiber itself. So we're able to talk about diffeomorphisms. Uh, and more precisely, we consider one diffeomorphism for each path. That depend on that depend smoothly on gamma and that belong to G. Now the last two conditions need an explanation. So let's explain those. Okay, so first of all, what does it mean that F gamma belongs to G? We're able to to identify every fiber with the standard fiber, but not unique in a non-unique way. We uh, uh, we were able to choose some identification, but this is well defined up to the action of an element of G. So in particular, well, let's draw a simple diagram. Let's take G and H elements of G. Uh, okay. Well, if uh, if I apply first first H, and then G, what do I get? I get the same as okay. So if I apply first H and then G, I get the same thing as uh, when I apply first G and then G H G to the minus one. So we um, uh, um, we don't really have an action of G on each fiber, but we have an action up to conjugation by an element of G. And the result, as a result, we have a preferred class of diffeomorphisms between two fibers the same path component of V. Namely, we identify each of the fibers with the standard fiber F. And then we have well, for every map from one fiber to the other fiber, we get a map from F to F. And if this map is induced by an element of G, then we say that the map of the fibers is induced by an element of G. And this is well defined, although the action of G on each individual fiber is only defined up to conjugacy. So, for example, there is no preferred, if we have a vector bundle, there is no preferred action of GLN R or GLN C on the fiber of the vector bundle. Why? Well, because we don't have a basis. We don't have any natural basis in the fiber of a vector bundle. But what we do have is linear maps. If we have a map from well, the fiber of a vector bundle is a vector space. So if we have a map from the fiber to itself, we're always able to tell whether or not this map is linear. Okay, I'll write this down. Okay. Are there any questions? Okay, now the second thing we need to explain is what does it mean that the diffeomorphisms depend smoothly on the path. Well, there's a standard trick of defining smoothness in the infinite dimensional case. Let's uh, okay. Let's take XY smooth manifolds. Let's well, I've already used F and I've already used G. So what I do? Okay, let's say H. And let's take another smooth manifold Z. Sorry, undo. I want to say what it means for a map from C infinity x y to z to be smooth. Well, there's a simple trick. Okay, well, hopefully we'll be able to finish this before we get the boot. The trick is very simple. We use the evaluation. So, a map from C infinity x y to z is smooth if and only if
So it is a map from something infinite dimensional to
yes,
smooth manifold.
it's a map from the set of C infinity maps from x to y. And by the way, it's infinite dimensional, but it's it's not a particularly badly behaved infinite dimensional space. In particular, if we introduce the right topology on the space, then the space will be will deformation retract onto a locally finite polyhedron. So from the homotopy point of view, these spaces are sensible. They're not. There are much worse spaces than these. Okay, so we want to define smooth maps. So for every smooth manifold, W. Okay, I think I've uh, okay. I'll finish writing the definition, and then I'll change something and I'll so first I'll write the definition, and then I'll see what this then we'll see what this definition actually defines. So we have the evaluation map, which is um, uh, um, no, yes. Okay. Let me change the order. So I have X, Y, Z smooth manifolds. Okay, I'll raise W. Okay, I start with the map from Z to C infinity X, Y, and I want to be able to say when this map is smooth, and the the trick is to use the exponential lemma. And transform this map into a map from X cross from Z cross X to Y, and this is a map of finite dimensional manifold, so it makes sense to require this. Okay, now we know what a smooth family of what a smooth map from Z to C infinity x y is. Okay. Now. Well, now we have a family of diffeomorphisms f gamma, and f gamma goes from E gamma naught to E gamma 1. What does this mean for what does it mean for this family to be smooth? This means well, we're running out of time. This family depends smoothly on gamma if okay, we have less than 1 minute left, so yes, I've saved the notes. Let's disconnect and connect again, and we'll finish this part then.